Hello and welcome to this short session on RC circuits. Now, the mathematical behavior of RC circuits is well documented in electrical engineering textbooks, but the aim of this session is to try and develop a physical or an intuitive understanding into how these things work. With a view to this, let's take a look at the simplest RC circuit, which is a first order series combination of an R and a C. We'd like to plug in a signal at one end, let's call that Vin, and see what comes out of the other end. Let's call that Vout. Now, in some cases, the input signal Vin could be a time-dependent signal, in which case the output for a simple RC circuit would also be a time-dependent output. Some examples of these time-dependent inputs could be a ramp or a step. This circuit's response to a step input is well known and is given by V0, where V0 is the magnitude of the step applied at the input multiplied by 1 minus exponent to the power of minus t divided by r into c, where t is the independent variable denoting time. The RC product is given the name tau and is referred to in literature as the time constant of the circuit. And to get an idea of why the term time constant is used, let's plot this equation using a small computer program to see what the output actually looks like. The red waveform here denotes the input, the blue the output, and we have some sliders to allow us to change the value of R and C in real time. Decreasing the value of R makes the blue waveform, that is the output, respond in lesser time, that is reach its final value faster. Increasing R makes the circuit takes more time in responding. Decreasing C exhibits exactly the same behavior as decreasing R. It should become evident by now that increasing either R or C would make the circuit slower in responding. This behavior is mathematically quantified as tau, or the RC time constant, and it says that if the time constant is large, then the circuit is sluggish in responding to the input, and a small time constant would enable the circuit to respond quickly to a given input. Now, that's as far as the math goes, but to understand intuitively what happens, we have to take a look at the behavior of the resistor and the capacitor components. Now, the resistor has a governing equation V equal to IR, which says that if a potential V is applied across its ends, then it will respond by sending a current through its ends. If we increase the potential applied across the device, the current through the device will proportionally increase or decrease as the case might be. For a capacitor, the governing equation is slightly different, and it says Q equal to CV, which is a way of saying that the voltage across a capacitor is directly proportional to the charges on the plates of the capacitor. If we try pushing a current through the capacitor, no current can conventionally flow because of the dielectric between the plates, but since current is the rate of flow of charges, we will have charges getting deposited on the plates of the capacitor. In a sense, the Q will increase as will the V across the capacitor. Now let's examine our circuit in the light of this newfound knowledge. Let's put up a graph on the right hand side of the screen with the time as the x-axis, and let's plot our input step with the magnitude of V0. To physically understand what is going on in this circuit, we're going to slow down time a bit by chopping up our time axis into equal time slices, call all of them delta t, and figure out what's happening in each of these time slices. Now, the node marked in blue is our output node, and the node marked in red is our input node, and we'll be drawing the waveforms in those same colors. It's a good time to point out to you, while we are making some space on the screen, that the blue node is also the voltage across the capacitor, and the red node minus the blue node is the voltage across the resistor. Let's give these some names, T1, T2, T3, T4, and so on, just to identify them a little better. Time t equal to 0, which is when nothing has happened to the circuit. The potential at the input node is 0, no signal has been applied, and the potential at the output node is also 0, assuming an uncharged capacitor. Now, this would more correctly should be called t equal to 0 minus, which is the instant right before the input has been applied, and we will call the instant right after the input has been applied as t0 plus, where, as you can check from the graph to your right, the step has been applied and the potential has suddenly jumped to V0. Now, since the capacitor doesn't let a potential change quickly across itself, it will pretty much remain at zero. Now, the potential difference across the resistor, which is V in minus V out, or the red node minus the blue node, has changed drastically. At time t equal to 0 minus, it had a value of 0 minus 0, which is 0. But at time t equal to 0 plus, it suddenly sees a huge potential across itself of namely V0 minus 0, or V0. Now there is a huge potential difference across the resistor, and since V equal to IR, it will respond with a current through itself, true to its name. The capacitor, on the other hand, will not let this current through, as has been discussed earlier, but will take the charges pumped in by the current and deposit it on its own plates. The capacitor voltage now rises, and since that's also the output voltage, we can plot it on the graph as having risen to some value. Let's call it V1. Updating these values on the circuit diagram, we have the potential difference across the resistor now taken on a new value. So at the end of time slice delta T1, the potential difference across the resistor is V0 minus V1 as opposed to V0, which was what we had at time t equal to 0 plus. Now if you notice, the potential difference across the resistor is now reduced than what it was earlier. Therefore, the current that it lets through also is reduced. Charges still get deposited on the capacitor, but now because of the lesser current, they get deposited at a lower rate, which means that the capacitor voltage still rises, but rises at a rate which is more gradual than what we had in delta T1. So at delta T2, it rises slower, takes on a new value of V2, and if we update these values, these node voltages on the circuit diagram, we have V2 at the output, V0 at the input, and at the end of time slice delta T2, the resistor sees a potential of V0 minus V2, which is even further reduced than what it was at the end of delta T1. Lesser current now is pumped in by the resistor. Therefore, the rate of charges accumulating on the capacitor is slower, the rate of rise of voltage across the capacitor is slower, takes on a new voltage V3. If we keep on repeating this operation, it becomes apparent that at each time slice, the potential difference across the resistor becomes smaller and smaller, which means that the charges pumped into the capacitor in that time slice become slower and slower. The capacitor voltage therefore keeps rising, but more gradually at each time slice. Now the voltages marked in blue show how the output voltage or the capacitor voltage has developed with the passage of time, and to its right, the expressions in green denote the voltage across the resistor, which is really nothing but V in minus V out. If we keep on plotting the output voltage of the capacitor, no points for guessing that the rise becomes more and more gradual with each passing time slice, and if we complete it, this is what it looks like. Zooming in and looking hard enough and bringing back the output from our computer program earlier, we see that we have managed to bypass the math entirely and plot the graph. Well, that's all, folks.